Hello and welcome back to Calculus 1, section 2.3, calculating limits. We're going to use algebra to manipulate the expressions and eventually compute limits. Before we do any of those, we can calculate every limit using what we learned last time, which is the chart, or look at the graph in some cases. So you understand also that from pre-calculus, right? You have your graphing, which is you shift function left, right, and all the other ways. But then you can also use the middle school method when you pick some x's and compute y's, right? And graph anything. So the same thing applies here. Now, we are going to look into the methods of computing limits. And from last class, you need to remember, you need to know that limits never compute at the point of interest. So if you're approaching 2, limits are never computing at 2. However, it turns out that if you are computing a function that has no vertical asymptotes or jumps and breaks and all these kind of things, plugging in is actually the way to go. I had this the first day where I said if f of x is equal to x squared, then f of 2 is 2 squared, which is 4, and you're done. And then I had the limit of x squared as x goes to 2 is also 4. So technically, yes, you can take this 2 and plug it in there and get the 4, but that's just because this is nice, okay? It's because it's nice. You can't always do that. What are you going to do if you have limit of 3 over x plus 2 and x goes to negative 2? Well, you're going to get 3 over 0, and then you can just cry because you can't solve it by plugging in. So when the functions are nice behaving, like any polynomial function, yeah, sure, go on and plug it in. But if you have a radical function, if you have a tangent or a cosecant, which have vertical asymptotes, if you have 1 over x with a vertical asymptote right at 0, you can't just plug in values. And we'll deal with those examples as well. So the first and the most basic method is clearly just plug it in, and if you get a value at the end without having zeros in the denominator or anything like that, you're done. So the way to compute the limit of, let's say, x squared minus 1 as x approaches 3 is to simply write 9 minus 1 is 8 and walk away. Now, it's okay to do that as long as you understand that this is actually wrong for limits, but it just works, so you can use it as a shortcut. In which way do we compute this limit? We hopefully understand that once you put your parabola down, whatever number 3 is, you have approach on the left and approach on the right, and they are going to converge at 8. So that is something that, you know, in the back of your hand, there is a concept behind the whole thing, and there is also the calculation, which is much easier to do this way than to go and, you know, do all the charts and do everything else. So yes, you are allowed to plug in, but you are allowed to plug in numbers only if you are not getting zeros in the denominator, or you don't get 0 divided by 0, or so on. So method 1, plug in. Disclaimer, does not work all the time. So immediately, here is the example where it doesn't work. So say you have limit of x goes to pi over 2 of tangent x. right? Well, sorry, the limit does not exist, right? And you can't plug in. You can't plug in because you will have a tangent of pi over 2. And the tangent at pi over 2, there is a vertical asymptote. Can't compute. Another example is limit x goes to 0 of 1 over x. Right? That's also can't compute. So the method can fail. I mean, method can work for the same functions if you have, let's change the color because we can, to gray. You can have limit x goes to pi over 4 for tangent x, in which case you just get tangent of pi over 4 and you get 1. So now it worked. Why? It worked because once you plugged in pi over 4, there was nothing weird happening with that function at pi over 4. The same thing if I have limit of 1 over x as x approaches to, let's say, 3, I'm just going to get 1/3. Right? So that's okay. But if I try to use this to find the limit when something weird is happening with the function, vertical asymptote, jumps, you know, and certain other things, we can't do it. So now, going back to the example, how do we compute the limit of, let's say, x squared minus 3x plus 5 divided by x plus 1 as x goes to 2? Well, you look at the denominator, right? You look at the denominator. And it's different than 0. So we're good, we're okay. We can just plug in. Means plug in. So what is this? It's 2 squared minus 3 times 2 plus 5 divided by 2 plus 1. So that's 4 minus 6 plus 5 divided by 3. That's what? 9 minus 6, that's 1. Hey, the limit is 1. We got it. Nothing weird was happening with the question. We did not have issue. So, we're done. If x approached -1, that's where all hell breaks loose. So, we have to deal with those cases now. So, what way are we going to use when we see the limit as x goes to 2 of, let's say, x squared minus 4 divided by x minus 2? Can I plug in? Sure, you can try. It won't work. What happens when I plug in 2? What happens? What do I get? I get 0 over 0. Right? Plug in. So can I plug in? Hell no. That's hell. There we go. Hell no. You can't plug in. You can't plug in because you are not getting an answer as 1 or whatever we had before. So in this case, we can use method 2, which is factoring. So now what you are going to do is going to go limit x goes to 2, and then it's x minus 2x plus 2 in the numerator divided by x minus 2. Cancel these, and your problem reduced to the limit x goes to 2 of x plus 2, which is, now we can plug in, right? Because no more denominators, no more zeros in denominator. Because there's no denominator to begin with. So now you can just plug in 2 plus 2 is 4 and move along. So we have the method now that will convert our limit, which we can't compute, into the one that we can compute by substitution, by plugging in, and just be done with it. Sounds good? Yeah. All right, next one. How about limit x goes to, let's say, 3 of square root give me a second when I make it juicy. Square root of x I know that the bottom I want to be x minus 3. That's cool. Yeah, let's do it like this. Square root of x minus square root of 3 divided by x minus 3. Why are you shaking your head? Nope. We can't plug in? Oh. So what should we do? Factor? How do you factor? How do you factor? What is the method that we can use? Anyone knows? Yeah, I see a lot of you doing this. What does this mean? Square root the whole thing. What do you mean square root the whole thing? You can't square because we have to square both sides. We only have one-sided. Anyone? Can you roll your R's? No, reciprocal is not ra. Rationalize. There we go. Rationalize, right? We can do that. So we multiply numerator and denominator. Did I just lose anything? What happened? Oh. By square root of x plus square root of 3 divided by square root of x plus square root of 3, right? And then we go and we say limit x goes to 3 x times x squared, so this becomes x minus 3, and in denominator we have x minus 3 times square root of x plus square root of 3. Now these cancel, and you are left with the limit 1 over root x plus root 3 as x goes to 3. So what's the answer? And now we rationalize this because we don't want square root in denominator. It's root 3 over 6.
That's conjugate?
Yeah, rationalize it by using the conjugate. Very good. Do anyone have sunglasses? Sunglasses, anyone? Oh, you have some?
I'm checking. I don't know.
You check. Oh, Oh, you don't have to. I promise not to ruin them anyway. I'll return them in. I am clean. Huh? I refer to this. I always forget to bring mine. Ready for the same problem? Let's do the same problem in another way. Pick blue. Let's go blue. Same problem. Limit x goes to 3, or square root of x minus square root of 3 divided by x minus 3. Now, what did you say earlier? Solve it by factoring, yeah. So can we factor this? Yeah, we can. You can factor anything you want. If it's on a paper, it can be factored. So, limit x goes to 3, and then you have your root x minus root 3, but then the denominator goes root x minus root 3, root x plus root 3. And then these cancel, and it's a one step to solve this. Boss. That's what the glasses are for. Yeah, this is the boss move, okay? Probably they don't, right? They're not good on it, right? They just say it.
No, they're not that bad.
They're not that bad. That's the way to say it's bad. Okay, because the word that, I just, you know. Actually, I'm gonna do more exercise now to return it. Do you see that we are immediately at this step, right? Without rationalizing, multiplying, and all of that kind of stuff. So apparently anything can be factored, right? Nice. I'm going to write this formula. So this is equal to the 3 dots, the root 3 over 6, same steps. So what are we going to learn? Ooh, let's use the space one. A minus B can be factored as root A minus root B, and then root A plus root B. This is algebra. So you're not used to this, but yeah. You can do all kinds of cool things with this. Five minus 3. Next time someone tells you, what do you know? You tell them that you can write number 2 as a square root of 5 minus square root of 3 times square root of 5 times square root, plus square root of 3. There you go. You know that. And many other things. So anything can be factored. You have x minus 10, not a problem. Root x minus root 10 times root x plus root 10. So this was a little side note that we can compute, that we can factor this way. But again, the problem can be solved using, right, by rationalizing. So method number 1, plug in. Method number 2, factor. Method number 3, rationalize. So maybe I write over here, method 3, rationalize. Good. But you see the same problem can be done by factoring as well. So let's take a look at limit laws. So assume limit f of x as x goes to a and limit g of x as x goes to a exist. C is a real number and m is larger than 0, n is larger than 0. So we'll need these. So these are some prerequisites. Okay, let's take a look at the limit laws. So number 1 is going to be the sum. And the sum says that if you have limit of f plus g, now this is all f of x and g of x. I'm just going to speed up through writing the whole thing. Is actually limit of f plus limit of g as x goes to a, obviously. Difference limit x goes to a of f minus g is limit f minus limit g. X goes to a, x goes to a. And the third rule that kind of belongs to this cluster would be the constant multiple rule, which says that the limit cf as x goes to a is c times limit of f. So you can do it this way. Now, these first 3 rules, I'm going to erase this now, but the first 3 rules help with a problem like this. Limit of 3x squared minus 2x plus 9 as x goes to 5. So the rules which are given to us as 1, 2, 3 helps us solve this in one step rather than, because the limit applies to each term independently, right? You see the addition of this is rule 1. You see subtraction over here is rule 2. And you also see 3 times x squared. That's rule 3. So all of the rules are used, and you can just say, okay, well, I work on this one separately from that one, separately from that one, and then I just put all of the answers that I get and combine them with the signs that were there originally. So those are the first 3 rules. They're very simply say, just, you can do everything term-wise. Rule number 4 is the product. And this one says that the limit of f times g as x goes to a is limit f times limit g. This is a very dangerous rule. It's correct, but you are not going to have this rule. So first 3 rules will also be there for derivatives and integrals. You'll see that. But this rule, oh, no. Multiplication is tricky with derivatives and integrals. So you have to be careful. 5, quotient. Limit of f divided by g is the limit of f divided by the limit of g. Again, x goes to a everywhere. Rule number 6 is the power rule, which says that the limit of f raised to the power of n, you can do the limit of f first, and once you get that answer, raise it to the power of n. They also have a fractional power, which it kind of belongs to combination between, rules 5 and 6, but fractional power. It says that the limit x goes to a of f that is raised to m over n is limit f right of x as x goes to a, and then m to the n power goes outside. Now it's important because in this particular rule, the denominator in the fractional exponent is all of the square roots and the cube root and the fourth root, right? So all of those. So I guess the rule's there. So these are the rules, and now you can use these rules to compute limits if you know individual limits. So let's do the example. Let the limit of f of x as x goes to 3 is equal to, see you next week, -5. And then limit of g of x as x goes to 3 is, let's say, 2. And the limit of h of x as x goes to 3 is, what is it? 4. Compute limit x goes to 3 of f of x minus g of x squared divided by 3 h of x. So the way we deal with this is we just employ the limit laws. So each one of these will have its own limit. So I have this division line, and then I have limit of f as x goes to 3 minus open parenthesis limit of g close parenthesis squared. And then we finally have 3 times limit of h of x as x goes to 3. And now you just replace them like blocks. I have other highlighters? Yes. So if you look over here, this block is this. So what replaces limit of f? -5. So this is equal to -5 minus, and now this is g, but g needs to be squared, so 2 squared, and then h is 4, 3 times 4. So we have -5 minus 4 over 12. This is -9 over 12, and when you cancel by 3 you get -3/4. I don't even know what f, g, and h are, but I was able to compute the whole thing because I had individual limits. We have the limit laws, we have plug-in, we have factor and cancel, we have rationalize, and then cancel. And then we have also the charts and graphs, if we need to, if we have to use them. So now, here is the example when you have to use the chart. So say you have to solve limit x approaches 2 of 5 over x minus 2. there is no way to get rid of the 0 in the denominator. And that's the problem. You can't rationalize this. There are no square roots. You can factor, but nothing cancels after you factor, so you're stuck, right? So there is nothing that you can actually do on this problem algebraically. So the methods that I've shown so far are not it. There has to be more, and there is. So what we do here for this particular limit is we go and we remember the theorem. For one-sided limits, which means the limit from the left, limit to the right. So what you do is you create your limit, x goes to 2 minus of 5 over x minus 2. You still can't compute, but you can do the chart. And the chart of values only approaches from the left. So this is just the red side, and you are approaching 2 from the left. And the way to approach 2 from the left is to go 1.9, closer, 1.99, closer, 1.999. And you compute these values. So 1.9 is going to give you negative 0.1, so negative 50. This is negative 0.01, so negative, is it negative 500, negative 5,000? Who cares, right? Let's say it's good. Don't worry about it. Anyone? No? Whatever? Okay, fine, whatever. So we see that the tendency of this is to go to negative infinity. There was no other way for you to compute this. That's it. It's negative infinity. And then you can do the other chart as x approaches 2 plus, which is from the right. X minus 2. And you have the same chart, but now your 2 is on the left side, so you can approach it from the right. And the far away, right, is 2.1, and then 2.01, and then 2.001. So what do you have? For 2.1, you have 50, and then you have 500, and then you have 5,000. So you see that the trend over here is to go to positive infinity. And now, since the two are not the same, limit x goes to 2, 5 over x minus 2 does not exist. So stare at this example a little bit and just realize that plugging in didn't work, factoring doesn't work, rationalizing doesn't work. Like, none of the methods and techniques we've seen, none of them work. So you have to resort to what I refer to as a middle school method, right? You pick your x's, you compute y's. So that was the most fundamental graphing, and everything else you did, right? You pick the values and so on and do it. So one more concept and the lesson is over. This one is called the squeeze theorem. Also known as the sandwich theorem. So it has two names. So the squeeze theorem, also known as the sandwich theorem. First of all, the concept of a sandwich, just in case. I'll just get pieces of bread over here. So you have a piece of bread, another piece of bread. Take a slice of cheese, put in between. If you're allergic or something, put 2 slices. Boom. Sandwich. Now, what we are going to do is we are going to sandwich the function that is not behaving nicely and we can't find the limit. We're going to sandwich that function with 2 functions that are easy to deal with. But it's important to mathematically construct those 2 functions that we can deal with, and they need to sandwich in the one that we can't deal with. Now, the simple idea is you don't actually hold the sandwich for the cheese, you hold it for the bread, right? And wherever you move the bread, the cheese goes with it. So that's the idea of trapping the function in the middle. So now, when I'm going to write the theorem, which is a lot of words, but when I draw the picture will be clear, and then we'll do the example. So here we go. The theorem says, assume f of x is less than equal than g of x less than equal than h of x. So we see that the g of x is sandwiched, right, in for all x near a except possibly at a. If limit x goes to a of f of x is the same as the limit x goes to a of h of x equals some finite value L, then the limit of the g of x, which is sandwiched in between, will be that value L. So, here's your f, here's your g, and here's your h on top. Technically, the way I look at this as a visual person is I say that these 2 functions sandwiched in the one in the middle, so wherever the y values, whatever the locations are for the 2 easy functions, because the one is squeezed in between, that's its location as well. What kind of location? Again, limits compute the y value of the function. So technically, y value of f, y value of g, and y value of h, they all coincide in the same y location on the graph. So, you have no idea. Keep your distance. So, thinking about the graph, you have a function that goes, right? And good luck finding the limit of this at, let's say, this point here. So you might be, and this is your g of x, right? The one that it's not behaving. So how about we find a function that traps it from the top and call that function f of x? No, that should be h of x. That's the one on top. And then, is there anything else interesting over here? Wood. All right. This one is your f of x. So hopefully you see that they all meet at the same location in terms of y elevation. So let's do this in the example. What is the limit as x goes to 0, I guess? Yep. Limit x goes to 0 of x squared sine 1 over x. What's the limit? Yeah, right? Good luck. You want to plug in? Sure. Sine of 1 over 0 is? What's 1 divided by 0? So you see, you can't compute, right? And I also have to discourage you right on what is this, class 3 that we have? I need to make sure that you are not going to make the argument, well, x squared is 0 times whatever the sign is 0, because 0 times anything is 0. You'll have to retire that way of thinking in calculus, because in this course, eventually in chapter 4, we are going to divide 0 by 0 essentially and get 3/4 or 1/2 or 5/3 or 0 or infinity. So certain problems, when you plug things in, will give different numbers, but they will all be 0 divided by 0. And then we are going to multiply 0 times infinity also in chapter 4 in one of the lectures, or in the same lecture. And there you are going to get a 0 or infinity or 3/4 or -1/2, right? It's going to be, or 7, right? We can actually make those problems to give you any answer. And that's a little bit scary. So unfortunately, we can't make the argument that 0 times anything is 0 and walk away, because I can rearrange the functions in different way, and then that product can give you something that 0 times whatever gives you 3/4, and all of a sudden your whole argument goes to hell, right? So we have to deal with this using the definition up here. Great. Let's build our functions, f and h, the bread functions that will trap g. This is g. This is the evil one. All right? That's g of x. I use a different color. How about this green? G of x. All right? So where do I begin? Well, I begin by understanding that sine of whatever you put in here, in this case is 1 over x, is bounded by 1. Because the range of sine x is -1 to 1. It doesn't matter what you pick. It has infinite domain. It doesn't matter what value you pick and you plug in, the function is bounded from -1 to 1. You can never get 1.1. You can never get 10. You can get anything between -1 and 1, including, obviously, -1 and 1. So now we're going to take this inequality and write it as -1 less equal than sine 1 over x less equal than 1. So we're just, instead of writing it with absolute values, we write it out this way. And now you compare what you have with what g of x is, because g of x needs to be in the middle. And you quickly realize that the difference between two is what? X squared. So x squared, x squared, x squared. You multiply everywhere by x squared. It's a three-sided inequality. You multiply throughout with x squared. And what you get is -x squared less equal than x squared sine 1 over x less equal than x squared. Whew. We trapped this really bad behaving g of x function. What do I mean bad behaving? Look at it and the graph on the over there. The one line that really oscillates in the middle, that's your x squared sine 1 over x. And you see that it goes into infinite oscillation in the middle where we are looking for the limit. You can't compute that infinite oscillation there. infinitely, it oscillates infinitely fast. So when you go back to this graph now, the sandwich theorem or the squeeze theorem says that, hey, I can deal with this and I can deal with this. I know what the limit x goes to 0 of negative x squared is. It's 0. And I also know what the limit x goes to 0 of x squared is, which is also 0. And now, happy? By the squeeze theorem, limit of whatever is trapped in between is also 0. So pretty. I have to make a point of using this much more. Makes all sparkly. And that is it. Yeah, I hope you're not disappointed. It's the way to compute limits. I don't have a microphone to draw up or anything. I just end the